Bismillahirrahmanirrahim. Assalamu alaikum. Today we will study Compton Scattering. Niels Bohr and Max Planck, two founding fathers of quantum theory, each received a Nobel Prize in Physics for their work on quanta. Einstein is considered the third father of quantum theory because he described light as quanta in his theory of photoelectric effect, for which he won 1921 Nobel Prize. Arthur Woolley Compton was born on September 10, 1892 and died on March 15, 1962, was an American physicist. He won Nobel Prize in Physics in 1927 for his 1923 discovery of the Compton effect, which demonstrates particle nature of electromagnetic radiation. The Compton effect is the result of high-energy photons colliding with the target, which releases loosely bound electrons from the outer shell of the atom or molecule. The scattered radiation experiences a wavelength shift which cannot be explained by classical wave theory. The effect is important because it demonstrates that light cannot be explained purely as wave phenomena. Light must behave as a particle to explain Compton scattering. By classical theory, when electromagnetic wave is scattered off atom, the wavelength of the scattered radiation is expected to be same as incident radiation. According to wave theory, X-rays are electromagnetic waves. If X-rays of frequency nu are incident on a material, they cause electrons to oscillate at the same frequency nu. Thus, the oscillating electron re-radiates electromagnetic waves with the same frequency nu as that of incident electromagnetic wave. Further, the electron in the material radiate uniformly in all directions. Thus, as per wave theory, the scattered radiation should have the same wavelength as that of incident radiation. The wavelength of the scattered radiation should not show any dependence on scattering angle. The classical wave theory fails to explain Compton's experimental result. To explain the shift in wavelength, Compton used Einstein's idea of light as a particle. Coherent scattering, also known as relay, elastic, or classical scattering, occurs when low energy radiation triggers all the electrons in the atom to vibrate at the same frequency as the incident photon. This in turn emits radiation of same frequency in all directions. Relay scattering of sunlight in Earth's atmosphere causes diffuse sky radiation, which is the reason for blue sky of the daytime and twilight sky, as well as the yellowish or reddish hue of low sun. The scattering caused by tiny air molecules increases as the wavelength of light decreases. Violet and blue have shortest wavelength and red has the longest wavelength. Therefore, blue light is scattered more than red light and the sky appears blue during the day. At sunrise or sunset, the sunlight travels a longer path through the atmosphere to reach our eyes. The blue light scatters the most and has been removed, leaving the red remaining to reach our eyes. Compton effect occurs due to the interaction of photon, X-rays or gamma with free electrons or loosely bound valence electrons. The incident photon is scattered and imparts energy to the electron. The scattered photon will have different wavelength and thus different energy. Energy and momentum are conserved in this process. In photoelectric effect, a photon interacts with inner shell electron of the atom and removes it from its shell. Pair production results in complete attenuation of incident photon. As the photon interacts with strong electric field around the nucleus, energy gets converted to matter, producing one electron and one positron. At low energies, photoelectric effect is dominant. This phenomena holds true until 511 keV, When Compton effect begins to dominate photoelectric effect, from about 511 keV to 10,000 keV, Compton scattering is the dominant effect. Above 10,000 keV, the dominant effect is pair production. Pair production only occurs when incident photon energy is at least 1022 keV. The experimental setup is simple. Monochromatic X-rays with wavelength lambda are incident on a sample of graphite where they interact with atoms inside the sample. They later emerge as scattered X-rays with wavelength lambda prime. A detector placed behind the target can measure the intensity of radiation scattered in any direction theta with respect to the direction of incident X-ray beam. The scattering angle theta is the angle between the direction of the scattered beam and the direction of incident beam. In this experiment, we know the intensity and the wavelength lambda of the incident beam, and for a given scattering angle theta, we can measure intensity and wavelength lambda prime of the outgoing beam. Typical results where the x-axis is the wavelength of the scattered X-rays and y-axis is the intensity of scattered X-rays measured at different scattering angles. For all scattering angles except theta is equal to 0, we measure two intensity peaks. One peak is located at wavelength lambda, which is the wavelength of the incident beam. The other peak is located at some other wavelength lambda prime. The two peaks are separated by delta lambda, which depends on the angle theta of the outgoing beam. This separation, delta lambda, is called Compton shift. As given by Compton, the explanation of Compton shift is that in target material graphite, valence electrons are loosely bound in the atom and behave like free electrons. Compton assumed that the incident X-ray radiation is a stream of photons. An incoming photon in this stream collides with a valence electron in the graphite target. In this course of this collision, the incoming photon transfers some part of energy and momentum to the target electron, and the scattered radiation has longer wavelength, smaller frequency, and lower energy. Compton derived the expression for Compton shift by treating photon and electron as relativistic particles. He used the principle of conservation of momentum and conservation of energy. It is a very elegant derivation and it explained the experimental results beautifully. According to special theory of relativity, any particle in nature obeys the relativistic equation E square is equal to P square C square plus M naught square C to the power of 4. M naught is the rest mass of the particle, E is the energy, P is momentum, and C is the speed of light. Photon has zero rest mass, which means M naught is equal to 0. Therefore, we get energy is equal to Pc. We also know E is equal to h nu, where h is Planck's constant and nu is the frequency. Therefore, h nu is equal to Pc, where h is Planck's constant, nu is the frequency, P is the momentum of the photon, and C is the speed of light. We all know C is equal to nu lambda, where nu is the frequency, lambda is the wavelength, C is the speed of light. Therefore, we get the expression P is equal to h over lambda, where P is the momentum, h is the Planck's constant, and lambda is the wavelength. Therefore, extra energy and momentum before scattering, energy E is equal to h nu, where h is Planck's constant and nu is the frequency. Momentum P is equal to h over lambda, where h is Planck's constant and lambda is the wavelength. Electron is initially at rest, which means initial velocity is equal to 0. Therefore, energy of electron E naught is equal to m naught c square, where m naught is the rest mass of the electron and c is the speed of light. Since velocity is equal to 0, momentum of electron Pe is equal to 0. Now let's see energy and momentum of photon after collision. Energy of photon after collision E prime is equal to h nu prime, where nu prime is the frequency of photon after collision. The momentum of photon after collision P prime is equal to h over lambda prime, where h is the Planck's constant and lambda prime is the wavelength of photon after collision. Loss of photon energy is equal to gain in electron energy. H nu minus H nu prime is equal to Ke, where Ke is the kinetic energy. H nu is the energy of incident photon and H nu prime is the energy of the scattered photon. Energy and momentum of electron after scattering. The energy of electron after scattering EE is equal to under root PE prime square C square plus M naught square C to the power of 4. PE prime is the momentum of the electron after scattering. M naught is the rest mass of the electron and C is the speed of light. Momentum of electron after scattering Pe prime is equal to 1 over C under root E square minus E naught square, where E is the energy of electron after scattering and E naught is the rest energy of the electron. If you notice, both equations of energy of electron and momentum of electron after scattering are the same. They just have been rearranged. We will use the principle of conservation of momentum. Momentum is a vector quantity, therefore we will take direction in notice. We will first consider the horizontal component of momentum. P plus PE is equal to P prime cos theta plus PE prime cos phi. P is the momentum of incident photon. PE is the momentum of electron before collision, which is equal to 0 since the electron is at rest. P prime is the momentum of scattered photon. Theta is the angle between the scattered photon and incident photon. Pe prime is the momentum of scattered electron. Phi is the angle between the scattered electron and incident photon. Initial momentum of electron Pe is equal to 0 since the electron is at rest. We will rearrange the equations and then we will square it. Using simple equation C is equal to nu lambda, P is equal to H over lambda, we find Cp is equal to H nu. Similarly, C is equal to nu prime lambda prime and P prime is equal to H over lambda prime. We find that Cp prime is equal to H nu prime. If we substitute Cp is equal to H nu and Cp prime is equal to H nu prime, we get the equation bracket h nu minus h nu prime cos theta bracket close square is equal to bracket e square minus e naught square bracket close cos square phi. Now let's consider the vertical component of momentum. The equation that we get is P prime sine theta is equal to P e prime sine phi. P prime is the momentum of the scattered photon and P e prime is the momentum of electron after collision. We know P prime is equal to h over lambda prime, where h is the Planck's constant and lambda prime is the wavelength after scattering. Pe prime, the momentum of electron after scattering, is equal to 1 over c under root E square minus E naught square. We will take c to the other side, therefore we get hc over lambda prime sine theta is equal to under root E square minus E naught square sine phi. We know hc over lambda prime is equal to h nu prime. Therefore, we get h nu prime sine theta is equal to under root E square minus E naught square sine phi. We will square both sides. We now have two equations, one from the horizontal component of momentum and the other from the vertical component of momentum. If we add both equations, we can simplify them as cos square phi plus sine square phi is equal to 1. We will use the formula bracket a minus b bracket close square is equal to a square minus 2ab plus b square. We will use it to open bracket h nu minus h nu prime cos theta bracket close whole square. Once we do that, we can use the formula cos square theta plus sine square theta is equal to 1. The final equation that we get using conservation of momentum is E square minus E naught square is equal to bracket H nu bracket close square minus 2 bracket H nu bracket close bracket H nu prime cos theta bracket close plus bracket H nu prime bracket close square. Using the principle of conservation of energy is much simpler since energy is a scalar quantity and we do not have to take direction into consideration. The equation that we get is E plus E naught is equal to E prime plus EE. E is the energy of photon before collision. E naught is the energy of electron before collision. E prime is the energy of photon after collision. EE is energy of electron after collision. The energy of photon before collision is equal to h nu. The energy of electron before collision is equal to m naught c square, where m naught is the rest mass of the electron. The energy of photon after collision is equal to h nu prime. The energy of electron after collision is equal to under root pe prime square c square plus m naught square c to the power of 4. We will square both sides and cancel m naught square c to the power of 4. We will substitute the value of pe prime square is equal to 1 over c square bracket e square minus e naught square bracket close. The final expression that we get using conservation of energy is square bracket nu minus nu prime bracket close square plus 2h bracket nu minus nu prime bracket closed m naught c square is equal to e square minus e naught square. The expression that we got earlier using conservation of momentum e square minus e naught square is equal to bracket h nu bracket close square plus bracket h nu prime bracket close square minus 2 bracket h nu bracket close bracket h nu prime bracket close cos theta. We will equate both equations that we got from conservation of energy and conservation of momentum. After opening the brackets and simplifying, we easily get the expression that we were looking for. 1 over nu prime minus 1 over nu is equal to h over m naught c square bracket 1 minus cos theta bracket close. If we want the expression in terms of wavelength, lambda prime minus lambda is equal to h over mc bracket 1 minus cos theta bracket close. Delta lambda, the change in wavelength, is equal to lambda prime minus lambda is equal to h over m naught c bracket 1 minus cos theta bracket close. H over m naught c is equal to lambda c, that is the Compton wavelength for electron. Here h is the Planck's constant, m naught is the mass of the electron, c is the speed of light, and lambda c comes out to be 2.43 into 10 raised to power minus 12 meters. The wavelength shift is at least 0 for theta is equal to 0 and at most twice the Compton wavelength of electron for theta is equal to 180 degree. Let's look at the small Python code that I wrote for Compton shift. We will import numpy as np. From matplotlib, we will import pyplot as plt. We will import some constants h, c, m underscore e. H is Planck's constant, c is the speed of light, m underscore e is the rest mass of the electron. We will take the value of theta from 0 to pi in radians with an interval of 0.01. X is equal to 1 minus np cos theta. We are importing cos from numpy and theta we are taking from 0 to pi with an interval of 0.01. Compton underscore wavelength is equal to h over bracket m underscore e multiplied by c bracket close multiplied by 10 to the power of 10. H is the Planck's constant, m underscore e is the rest mass of the electron, c is equal to the speed of light, and we are multiplying it 10 to the power of 10 to get Compton underscore wavelength in terms of angstrom. Difference underscore wavelength is equal to Compton underscore wavelength multiplied by x. We can find the slope by using polyfet from NumPy. However, if we analyze the equation, difference underscore wavelength is equal to Compton underscore wavelength into x. Compton underscore wavelength is a constant and is the gradient of the graph of difference underscore wavelength and x. We can round the slope that we found using polyfit from NumPy to 6 decimal places. We can print the gradient of the graph of difference underscore wavelength and x. We can find max delta lambda is equal to function max bracket difference underscore wavelength. We can round maximum delta lambda to 6 decimal places. We can print maximum wavelength shift in terms of angstroms. We can plot the graph of x and difference underscore wavelength. We can put title on the graph and x label and y label on the graph. The gradient of the graph comes out to be 0.024263 angstrom. This is the Compton wavelength of the electron. The maximum wavelength shift is equal to 0.048526 angstrom and is twice the Compton wavelength. The maximum value 1 minus cos theta can have is 2 when theta is equal to 180 degrees. Therefore, the graph of delta lambda and 1 minus cos theta is a straight line with a gradient of Compton wavelength. To convert the angle from radian to degree, we multiply theta by 180 and divide it by pi. Therefore, angle degree is equal to theta multiplied by 180 divided by pi, which was imported from NumPy. We can plot the graph of angle degree and difference underscore wavelength. The graph of delta lambda and theta looks like this. The maximum wavelength shift occurs at theta is equal to 180 degree. At theta is equal to 180 degree, the maximum wavelength shift is twice Compton wavelength. May Allah bless us all. Thank you for watching. Allah Hafiz.